Hello friends, I am Saroj Vishwas, gold medalist, first rank holder of 1994 batch in engineering stream of all the colleges affiliated to University of Mysore during that period. A BE in civil engineering from National Institute of Engineering Mysore, a MTech in structural engineering from Indian Institute of Technology, Delhi, that is IIT Delhi, a Sun certified Java programmer, Sun Microsystem USA. I have more than 25 years of professional experience in designing building structures and allied subsidiaries. I invite you all to learn with me how to design building structures using commercially available structural softwares with the help of some manual computation as and when needed. In these sections, we shall learn modeling of the geometry of the structure, that is, we shall model this hypothetical building. The modeling could be done right from the scratch, but we shall use a template file. To get this template file, you can go to this URL shown on the screen. It may not be available in Google search because this website is pretty new. So you have to write this URL address in the address bar of the browser. Also, I would request you to go to the help menu of STAAD Pro. There are various tutorial available. If you practice those tutorial, it will give you a fair idea about how to create the geometry of the structure, how the loading has to be done. So there are 3 tutorials, you can go through them. It will give a hands-on on the modeling. We shall open this folder. We shall double click this template. The STAAD Pro will open up. The file is now saved as HIP building. Now we shall go to the grid making icon. Edit this grid. Go to exit. Now it will be exit. So our building is 12 meter by 12 meter. So I put 12 here and then 12 here. So okay. Now snap node and beam. We create a 12 meter line here. Press Control. Go to 0, 0. Then create another 12 meter line. Close the snap node beam dialog box. So we have this beam. I am not using this grid line to create my buildings. I have taken help only to create my first 2 lines. This is because we might not be able to create unequal grids in STAAD Pro. So now to place my buildings, to create my building, I copy this line and go to paste beam. There will be a reference line. I pick a base point and then press Shift K. The node will be seen. Click here. Press OK. This member is now generated. Now press Escape. Select this, copy it, paste beam, take base point, reference point, and select it here. Now we have 3 ways along Z direction. So we shall insert 2 nodes here. Add 2 nodes. Add 2 nodes. We have 2 bays along X direction. So insert midpoint. Now STAAD Pro doesn't show the column location on plan views. So we shall, to address this these things we shall assign support to this node, so that whenever we go to a plan view or where is our column is known to us, we shall later delete it when we will run analysis. Go to general, we'll find support icon, create support, fix support, add. The support is added, select the support, then click all the node, click assign. Now we knew our first floor column heights are 3.125 meter. So select this node, go to geometry, translation repeat, y direction 3.125, link step, okay. So our ground history is created. Now we shall create the first story as well. Our first story is column height is 3.88 meter. So we select all this column, copy this, choose a base point, paste it over here. So we have second story created, but the column height here is now 3.125. So we need to increase it. So we have to increase it by 3.88 meter minus 3.125 is equal to 0.755. So I go to side view, select the top nodes, move in y direction 0.755. Okay. So our first story column heights have become 3.88. Now let us assign some standard section to these columns. So we'll choose from section database Indian, ISMB 450, add, then ISMB 550, add. So the column, these are the base second story where we'll have 12 meter clear span. Now we have two more columns at ground level. So I take this, copy this beam, paste, reference point, okay. I paste this beam here, then I take two columns from here, copy, paste beam, reference point, okay. So since these columns will have 12 meter span, clear span at above mezzanine floor, so we assign a greater size of column here, 550, assign, yes, and all the others column we assign as 450. Assign. So let us go to the mezzanine floor level. Select the node cursor, click a node on mezzanine floor level, node 11. We have now go to tool, cut section, exit plane, node 11, okay. So go to top view. So we have this view here. Now go to display node to node distance. Remove node to node distance. We have now select the beam cursor on select, create all the beams at the periphery first. These periphery beams are created. Now we have to create the main girders. These are the main girders. So this is our double height area. So we have created the main girders. So we need to have a secondary girder to support the stringer beam. So this should be around 1.35 meter plus 3 meter plus 0.45 meter. That should be 1.35 meters for landing area, then 3 meters for steps, then 0.45 meter from the last line of the riser. So we should create a beam 1.3 4.8 meters from right side. So I copy this beam, paste this beam in X direction minus 4.8. One of the secondary girder has been created, but these are not the column locations. So this position doesn't have any column. So we go to support, we assign them no support so that we remain in clarity that there is no support. Assign, yes. Now we need to create another secondary beam to contain the staircase cutout. So we copy this beam, paste this beam by measuring the distance from the architectural drawing. Where is 2 meter? It comes out to be around 1.33 meters in minus z direction. 1.33. Okay. So another secondary beam is created. So there is no column here. So I again assign no support here. So our main beam has been created. Main girder and secondary girder has been created. So I assign certain property. So the main girder, these girders shall be movement frame. So I will assign a bigger size of the member here. So I take ISMB 400. ISMB 400. Assign. Okay. This is assigned. Now close this dialog box. Then we have these secondary beams. Wow. These are also main beams, but these will be simply supported beam because we have concentric basing along Z direction. So we can afford to have simply supported beam in these directions. So it will not carry much of the dead load. We'll come to know how it is. It will not carry much of the dead load when you model the joist. So along with this, I assign the secondary girder also as a bit lesser section, say ISMB 350. Assign. Now we have the main girder property and the secondary girder properties has been assigned, and these will be our struts and ties around the column at mezzanine level. So I take tube section, pipe section here, go to Tata Structura, select circular hollow, around 100 mm nominal board pipe of medium size should suffice. So we assign these to these sections. So we need to discuss something about releases. In STAAD Pro, releases are assigned to make a beam ends rotation free. That is, whenever we want to make a beam not to behave as a having fixed support at the ends, we need to assign releases. So, for example, simply supported beam, we will assign releases about local z-axis at both the ends. So this will make the beam to behave as a simply supported beam. So wherever we provide shear connection, we usually releases those beams in about local z direction and local y direction. So you see these are the local z direction and local y directions of a member. This is local z direction, this is local y direction. So when you release about local z, mz, this movement resisting capacity is no longer exist. Then when you resist about y direction, this movement resisting capacity no longer exists. Now we shall assign the releases as required for the secondary beam and the beam along z direction. We shall release this beam along the z direction because we have concentric basing along to resist the lateral load here. So we really don't need a moment resisting frame, and also the orientation of the I column is such that we need to have shear connection for the members along z direction. So basically the I columns will be oriented in such that the members will be, these members will have to be connected from the wave. So making movement connection at the wave is from the wave is a bit difficult. So generally in design practice, we provide cleat connection from the wave for any member protruding out of the column from a wave. So first we select this member, go to command, member specification, release, start MIMZ, then again go to command, member specification, release, and MIMZ, assign. Now these are our secondary beams. So this beam will start of the beams is coming out of a main girder. So this beam has to be released at a start point. And this beam also has to be released at a start point. And this beam has to be released at end point. Note that we have wrongly assigned release at the end point of this beam and at the start point of this beam. And this will create a stability problem in the stiffness matrix of the stud, and this is the unstable position. So we have to remove this. We double click it, change release at end, MIMZ assign, close. So this release is removed. Now this is change release at start, MYMZ, assign, close. So this release is also removed. The next step is to create the joist at the Imaginary Pro level. We have already decided that we will place the joist at 1.5 meters center to center. Our beams, main girders are 6 meters, so we can insert 3 points here. So 1, 2, 3, 1, 2, 3. Insert node, add 3 point. Okay. So if we measure this distance, we see 1.5 meters center to center. Now go to the beam cursor. Take this beam. Make this beam. Now let us go to the property, because this will assign them a property, because it will help in copy pasting, because otherwise STAAD would say that the member has not been assigned any property. So we go to the property dialog box. We select section from the section database, Indian sections, ISMB 200, assign. Now the joists are actually simply supported beams, so we have to assign releases to this joist as well. So go to command, member selection, release, start, assign, and assign. Now we copy this beam, choose a base point, paste these beams here, here, here. Now for this purpose we have to copy another beam, copy, take a reference point at the bottom. Now on the other side, now paste it here, 1, 2, 3. Now we would require some joist here as well, because our deck sheet will be spinning like this. So the corrugation will be along this direction, so it has to span like this. So this require members at this position as well. Now you have to provide, go to geometry, add beam by perpendicular intersection. Now start and end of these beams are not in the desired direction. If we press shift, we can see the start and end. See the start, green part shows the start and the blue color shows the end of a member. But for this member, it is in opposite direction, showing it is opposite direction. So we do not want this. So select this member, go to tool, redefine incidence, switch incidence. Now these are also for a start and end incidence of these members are also in the direction of other joist members. So these are also joists, so I have to assign releases to this. So go to command, member restriction, releases, start MYMZ, end MYMZ. With this, our framing part of mezzanine is complete. Now we shall try to model the stringers of the staircase. Now go to view whole structure. The 3D view will come. Press shift E again. So start and end incident will no longer be seen. Go to top view now. Select the stack column containing the staircase portion. Select view only selected object. Selected object only. So go to 3D view again. So we have this view. As you can see, the staircase mid landing beam was 1.535 meter from the bottom, that is bottom of the base plate. To select these two members by pressing Control and then selecting, then insert node, right click, insert node, distance 1.535. Okay, so we have now the position for the landing beam to be created. So this is our landing beam. The landing beam will be also simply supported on. Let us assign property to the landing beam as well. Go to section database. Indian ISMB. Let us take ISMB 350 again. Assign. This has been assigned. So this will be again a simply supported command. Member restriction, release, start MOMZ, end MOMZ. Now we need to find the location of the stringer endpoints. So let us drop a perpendicular member geometry, add beam. So within these portions, our landing platform will be there. By arrow, using arrow key, you can rotate the model. If you press Shift X, then and close the property button, and press Shift X, the member sizes will not be seen anymore. So this is the part where the landing stringer will be there. Now let us select this part, insert a node, add midpoint. Okay, we have added a midpoint. Copy, paste, minus z direction 0.2. Okay, now move this selected part in z direction 0.2. So this has been moved. Let us remove node to node distances. So now again we copy this, paste node, z direction 0.2, and we copy this, paste node, minus 0.2 in z direction. Okay, so we have the endpoints or start points of stringers. So we now shall delete this beam, this member. Select this and press delete. So there is no intersection for these two members. We can join this member together. Go to command, go to geometry, merge selected members. These members will be merged. Now see this end release has been removed by STAAD Pro. So we have to assign it again. Command member specification, release. Close this box. You can see end. Assign. It has been assigned wrongly. So we need to redefine the incidence of this beam tool. Member restriction, redefine incidence. So the release it at proper place now. Now our landing is around 1.35 meter from the center line of grid 3. From grid 3. So let us copy it, then paste it along minus x direction, minus 1.35. So we have the positions for the landing. Now we need to know where the stop risers starting and ends starting. So we know it was from the figure. This is 3 meter. Click assign. Yes. Now the 3D view, go to the 3D cursor for this stringer. Now see the orientation of the stringers are not proper. We have to give a proper direction for these two stringers. These two stringers. So we close the 3D view. Now we select this members tool, member selection, redefine incidence, switch incidence of selected members. Now if we press shift E, we can see the staircase is starting from here, going there, going there. Then again it is starting from here and ending here. So press shift E again. Now go to property, go to select by property, by specification, property name, ISMC. ISMC will close this box and see the 3D view again. In the 3D view, you can see the orientation of both the stringers are in same direction. So we need to rotate this member and this member to have flanges in other directions. So let us close this 3D view. Now select this member, select this member, select this member, select this member and this member. Go to property, create beta angle 180 degree. Okay. -180°. Okay, this comes here. So we have to select these stringers again. Assign. Now let us select all the stringers again. Go to 3D view. They are in proper direction. Now we have to assign releases to the staircase stringers. Now the staircase stringer configuration is such that it forms a triangular formation, and whenever there is a triangular formation, tends to attract lateral forces. But we do not want this staircase stringer to absorb any lateral forces. So we have to release is fx direction along with my and mz to make these stringers simply supported. So we have to release fx direction at either at end or at a start. We shall release it at end. So for start point, we already have release command member specification release. We already have this release. Now for end point, we shall define a new command, member section release, and see now I am releasing the effects as well along with the MI and MZ assigned. So it will prevent the staircase to absorb any lateral load. For this part, you have to put, while detailing the connection, you have to put slotted hole for the board so that the staircase is free to move whenever there is a lateral, whenever the structure is subjected to some kind of lateral load. Now we have to make certain arrangement also. We'll insert certain nodes here. Copy, 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 paste node. Next direction, say around 0.3 meter. In negative x direction on 0.3 meter, copy, paste node, minus 0.3. We join these members with some forces. You can move the position of the staircase bit by rotate the model bit by using arrow keys. So we select, again we insert some node here, copy, copy, insert node, add a distance 0.3. Okay. So it will have deck slab. So we'll model the deck wave slab. So we'll insert another 2 sets of nodes here. Insert node at midpoint. Join them again. Join them. Now select all these members. Command member specification, geometry, go to geometry, add plate, create infill plate. So 7 new plates, 1, 2, 3, 4, 5, 6, 7. Now you have to assign some property to this plate as well. We know our equivalent depth of the concrete on above the deck slab is 1 or 2 mm. So we take point 1 or 2 mm. Now we do not want this concrete to have any density. So we select 0 density. It is already there in the template editor defined. So add, close. So we select the plate cursor, select all the plates. By selecting plate cursor, you can select all the plates. So assign. So we have the waste slab model. We'll later assign this waste slab as plane stress element so that it doesn't take part in flexural strength of the flexural capacity of the structure. Now let us Go to the view again, whole structure. We have this. Go to side view. These members we had created for helping us in creating the geometry, so we do not need this member. Probably the RCC foundation designer would require this member, but the steel designer would not require this member. This was created only just to help creating the geometry of the model. So we select this member, press delete. These members are deleted now. No, yes, okay. Now go to 3D view. Now let us go to the mezzanine floor also and create the deck slab. Node 11. Tool, cut section, exit plane, node 11. Okay. Go to top view. Let us select these two members and insert two members. Okay. So geometry, add beam by perpendicular offsets. Okay. There is probably two nodes created here, so we can actually merge them. Command, go to command, because they are very close to each other. Geometry, merge selected node, keep the last one. So now go to geometry again, add beam by perpendicular intersection. Take this, drop it here. Take this from grid 1, drop it to grid 3. Now select all the members, go to geometry, intersect. Okay. Now select these members. Select only those members which I am selecting. We are not providing any slab, grid slab here, because we do not want to be connected here to take part in taking lateral load. We should actually detail in structure also by providing some caulk here while pouring concrete. Whenever the STAAD asks you for saving it, we should keep on saving it. So go to geometry, create infill plate. So 42 new plates have been created. Now select the plate thickness, go to plate selecting cursor, select all the plates, assign. There is one part where the plate has not been created, we have to check it. So we can manually create it. Select the icon or add 4 noded plate, take it, move it anti-clockwise. So this, we have to assign property to this as well. Assign. Now go to view, whole structure. Let us see the 3D view. You can see the slab has been modeled, deck slab has been modeled. Close the 3D view. Now we shall select the members which we created in order to help us in creating these plate elements. So select member by missing attribute, missing property. So there is a lot of members also. These are the 2 columns which we did not assign any property probably. So we must assign the property to them first. So let us assign the property R1, R1 and R1. Okay. Assign. Now select by specification, by missing attribute, missing property. So we have all these missing properties. So Click delete. Now you have to assign this plate element as the plane stress. When you assign plane stress, the deck slab act as a semi-rigid diaphragm. Nowadays, no more a rigid diaphragm is assigned. Earlier days, a rigid diaphragm was assigned whenever there is a concrete deck slab or concrete slab. But nowadays, it has become practice to take semi-rigid diaphragm, which is actual. To know more about it, you can visit the website which I had shown on the URL. There is a detailed book on design of steel structure with STAAD Pro, and you can know more about it from that. So command plate specification, plane stress, select plane stress tab, assign. The plane stress has been assigned to this concrete plate element, so it will only carry now axial forces in lateral direction. It will not take part in flexural resistance, so it will not add strength to the flexural. It will not add any strength to the bending capacity of the steel beam or joist. So let us close this specification whole structure dialog box. Now we have to model the raptor. So we know the raptor to raptor distance is around 6 meters. So in PVA structure, generally 1:10 slope is taken. So we shall take same kind of slope. So let us move these two nodes. 6/10 is equal to 0.6. Move in y direction 0.6 meters. Okay. Now let us add these members. So we should assign, these are called raptor, as I have already told you before in last sections, or in the section where we planned the framing plan. Let us, these members will carry very light load and span is not much, so let us take Indian ISMB 250, add, assign. Now usually there will be some projections. So say about 4.45 meter from the steel line. Steel line is nothing but the outer cladding line. So if we assume that our steel line, our guts and purlins will be of 250 mm depth. A gut or purlin will look something like this. 250 mm depth, and we have to chosen our maximum column as 550. So this is 550. This is 250. And there will be steel line 45 mm with corrugation, and from that we have a projection of around 450 mm. So this is our I-beam. So the actual projection from central line of the column will be 550 by 2 plus 250. This is the width of the girth plus 45 mm plus 450. This works out to be 1020, that is around 1000 mm approximately, you can say. So let us copy this member copy, paste in x direction 1 meter, copy, paste in minus x direction 1 meter. Okay, so I copy this raptor, paste, reference point, copy, paste, reference point, geometry intersect selected members, intersect. Okay, this has been intersected. We select these nodes using node cursor, then press delete. We have the raptor assigned, so now we take this raptor, copy, paste, reference point. We have this reference point, Popo reference point. Okay, here 12 meters span, here 12 meters span, here 6 meters span. Now we have to model the strut and ties also at the periphery. So we have this strut and ties. We need to assign some properties from strut. Go to section database, data structura. Again we take circular section. No, where here we will take both circular section and square section, because at the periphery we have dry wall. Dry walls are made of light gauge steel frame which require a flat surface to have proper connections. So for certain member we will have a square hollow section, say 100, 104. Add then circular hollow section we already taken medium that will again take medium size nominal board, add. So select 100, 104 and select those member where there will be a dry wall, assign them. Now select this strut and this strut. Okay, this is 100 mm nominal medium size pipe, and these are tube sections. Now see, these are 11, 12 meter span, so we need to have a get up depth of raptor. So something similar to the size of the column we had taken earlier. So as of now we will take it 550 mm. Go to Indian sections, ISMB 550. Assign, close. Press Shift X so that number property is no longer shown. So we do not have any column here. So let us remove this support. Go to support. Select no support. Assign. Okay. Now let us go to the roof level view. Select the beam cursor. Select the beam cursor, select all the roof level and go to view selected object only. Go to 3D view. Now we need to assign some strut here. 1, 2, 3 at ridge level. And again we shall assign at this point also. Insert node, Add midpoint. So we'll assign the same start member of 114 here. 1, 2, 3, 4, 5. This has been assigned. Now we know we had roof bracing, so we should model that as well. Between grid B and C, we had planned the roof bracing to carry the lateral load. So we take circular hollow section of 114 again, add, go to select by missing property. You see there the raptor which has not been assigned. So let us attach. ICB2 we had selected but we did not assign. Let us assign it. These projections will also shorter members will do because this is only 1 meter cantilever. So a small size member will do. So now we again go back to 100 mm nominal bore pipe. Select by missing property, missing attribute, assign. So this has been assigned. Now view whole structure. Now let us go to the side view of grid 1. So node 1, go to tool, cut section YZ along YZ plane 1. Okay. Now we have to assign concentric bracing at this part between B and C. Concentric bracing. Now for this we will have tube sections because there will be some LGS members. Section database, Tata Structura, square hollow, 104 add, then circular hollow, 114 medium section nominal bore, 100 mm nominal bore add. Add. Let us select 100, 104 and assign them at story part above mezzanine, and then let us assign this part below mezzanine because this doesn't have any dry wall. Now go to view whole structure, select by property name, copy Reiki base point, reference point. Okay. Now we had earlier discussed that we have a different orientation of this column at intersection of grid D and 2, so that it can resist more lateral load. See, if you see the orientation of in 3D view, the orientation is like this. So we have to rotate this column as we had already discussed in framing plan. In property dialog box, go to bit angle, create a bit angle 90 degree. Okay, select this bit angle. Now select this column. Assign. Now see the part 3D view again. The orientation of this column is changed down. Tool, cut section, trim. So the mezzanine joist or accidentally deleted here. So what we can do, we can model them again. Property, we are taking as ISM 200. Assign. Okay. Save it. Save. Now command member selection, release, because these are joist members. Start, assign, end, assign. View whole structure. Now we can see the joist here. Okay. Now let us, our modeling is, geometry is complete. Now let us remove the supports. Select this support, delete. Now create a fixed support and provide this support at the start of end, staircase stringer. Now we have to create a hinge support. We are taking a hinge support for this wheel column. Assign this hinge support here, and we'll keep this wheel column released at top as well. Command member selection, release. Let us assign new release to this. Okay. Now again go to support, create, enforce but. What we told, we will have support released about MX axis. So we release MX, but all other things, FX, FI, FZ, MY, MZ is restrained. So add. So we are adding support in a similar manner we had discussed during framing plan, in the framing plan sections. Now you have to assign this strut and ties as truss member. Go to select by selection, property name, select 114, 100, 104, 114, 104, 114, 114. So all the truss, brace member, truss member, bracing members and strut and ties have been selected. So let us go to command member selection, truss, assign. We have assigned truss, so it will take both compression and tension. So we will be able to perform dynamic analysis, but a truss, as you know, truss section will not carry any kind of bending movement. So the connections designed for this members are to be designed accordingly to, so that its connection through the connections bending moments are not transferred to these members. Now modeling of our geometry is complete. So we have to test whether everything is working proper. So for that we have to start with self weight of the structure and give it a run analysis command, so that any error or something like that is known to us. Before that we must check certain checks. Go to tool, check for multiple structure. There is one structure, okay. Check for duplicate members, no duplicates members. Tool check for orphan node, highlight no orphan node, select, check for zero member, no zero length member. Tool, overlapping collinear member, no overlapping collinear member. Tool checked for improper. So there are actually nodes in between. So these plates are creating some. So this is not a issue. It will not impact the results. So we can ignore it, because there are plates in between. The plates corners are not matching. There are plates, and one plate here, only one plate. Plate here. So one plate is coming in between. So this red plate warning is coming in checking tool checking improper connectivity. So it is not an issue. So we have to now give it a run before with the self weight. So let us go to load and definition. From the template we already have dead load. So we usually assign 15% more dead load for bolted connections. So self weight will be 0.1.15. Add, assign to view. Okay, it has been assigned. Now let us go to load definition. These are the reference load definition. These are the load from which the seismic weight and seismic base shear is computed by the software. So let us add self weight here as well. Self weight. So for this we do not provide any sign. So 1.15. As I already discussed, there is no meaning of sign for dynamic analysis. So let us add it x direction, let us add it y direction. All the three directions will be required for dynamic analysis. So select it, assign to view, select it, assign to view, select it, assign to view. Now let us give it a run, go to analysis, run analysis. Do we want to run the analysis with empty load cases? Yes, as of now our template has all empty load cases except the self weight dead load part. Yes, save, yes, save. So there is zero warning. So our modeling of our geometry is okay. So with this we conclude the sections of modeling the geometry. See you in the next section.